In this lecture, I am going to consider a preliminary property that is involved with the Sturm-Liouville boundary value problem. So, first of all, I need to define what is boundary value problem, then what is Sturm-Liouville boundary value problem, and then a particular property of solutions of Sturm-Liouville boundary value problem. Suppose this is a second order ordinary differential equation, that is Lx equal to At x double dot t plus Bt x dot t plus Ct into xt equal to 0. This equation is defined over the closed interval a to b, where a and b are two finite real numbers, with the boundary conditions xa equal to 0 and xb is equal to 0. Now, these type of boundary conditions are called separated linear homogeneous boundary conditions. We need to understand each of these terms. In one condition, that is xa equal to 0, only endpoint A is involved, in other only the endpoint B is involved. So, therefore, they are separated. Of course, conditions are given at the boundary, so hence it is a boundary condition, and this function, that is x equal to 0 and xb equal to 0, that means the function x involved with both the boundary conditions, these are linear, and on the right hand side you have 0, so that is why it is homogeneous boundary condition. The most general form of linear homogeneous boundary conditions at A and B are actually of the form Vj xa xb x dot a x dot b, this is equal to 0. This is the homogeneity condition, that means, as, or you can say on the right hand side you have 0, that is why it is homogeneous, and here V is a linear functional of these four quantities xa, xb, x dot a and x dot b. Now, this is the general format. In the previous definition, as one condition is free from B, another condition is free from A, so hence they are separated. These V1, V2 are two linearly independent linear forms, so that means V1 cannot be written as some constant into V2. So, these are two linear homogeneous boundary conditions. Linear non-homogeneous boundary value problem is given by this one, Lx equal to dt, where Lx is already defined here. Keep in mind that non-homogeneous boundary value problem, this term non-homogeneous is related with the non-homogeneity of the differential equation, not of the boundary condition. This is a very important point. So, therefore, a non-homogeneous equation subjected to linear homogeneous boundary condition is known as non-homogeneous boundary value problem. Apart from this type of boundary value problem, we can have periodic boundary conditions also. Those are actually involved with Sturm-Liouville boundary value problem. That is why I need to mention it here. That is, value of x at left end is equal to value of x at the right end, that is xa equal to xb, and similarly x dot a is equal to x dot b. What is a regular linear boundary value problem? A linear boundary value problem, homogeneous or non-homogeneous, means the equation is either of the form Lx equal to 0 or Lx equal to dt, is called a regular boundary value problem if A and B are both finite and At not equal to 0 for all t belongs to A comma B. So, if these two conditions are satisfied, that means A, B are finite and At is non-zero over the entire interval A comma B, then either Lx equal to 0 or Lx equal to dt subjected to this type of boundary condition is known as regular linear boundary value problem. Finally, now we can define the Sturm-Liouville boundary value problem. We consider an ordinary differential equation of the form that is Pt multiplied with x dot t, its whole dot, that means ddt of Pt x dot t plus Qt plus lambda Rt into xt, this is equal to 0. So, this is a special kind of second order linear ordinary differential equation involving a parameter lambda. This is defined over the closed interval a comma b. Further, p dot t, qt and rt, that means three functions involved with this equation, they are real valued continuous functions on the closed interval a comma b, and lambda is a real parameter. If we further consider the boundary conditions in this particular format, that is m1 xa plus m2 x dot a equal to 0 and m3 xb plus m4 x dot b equal to 0, such that m1 and m2 are not simultaneously equal to 0. Similarly, m3 and m4 are not simultaneously equal to 0. This can be written mathematically as m1 square plus m2 square not equal to 0 and m3 square plus m4 square not equal to 0. So, this is a problem. This is the boundary condition. Here one boundary condition, that is the first one, does not involve B, second one does not involve A. So, therefore, again we can say these are linear separated homogeneous boundary condition. And for this type of problem, in order to define the Sturm-Liouville boundary value problem, apart from these two boundary condition, this additional condition is required to be satisfied, that is Pa equal to Pb. Now, if we consider a boundary value problem consisting with equation 2, so that means this equation, of course P, Q, R, they satisfy the required conditions like they are real valued continuous functions. Subjected to either the boundary condition 3 or the boundary condition 4 is known as Sturm-Liouville boundary value problem, and which is oftenly written in shorthand notation as SL-BVP. Sturm-Liouville, that is SL, and BVP stands for boundary value problem. Now we come to the solution of this kind of boundary value problem. Suppose for a particular value of lambda, x lambda is a non-trivial solution of the boundary value problem consisting with 2 and 3. So, 2 is the equation, 3 is the boundary condition, or equation 2 with boundary condition 4. Then lambda is called an eigenvalue and x lambda t is called the associated eigenfunction. Now, there are several properties of these eigenvalues and eigenfunctions associated with the Sturm-Liouville boundary value problem, but here within this limited time period I am going to emphasize on a particular property, that is the orthogonality property of eigenfunctions subjected to some condition. So, for that purpose we need the Abel's formula. Abel's formula states that suppose Ft and Gt be two solutions of the linear homogeneous ordinary differential equation this. So, that means it is a modified, or you can say rather reduced version of 2, that means in 2 if you substitute lambda equal to 0 you can get this equation 5. So, therefore, Pt x dot t whole dot plus Qt xt, this is equal to 0, this is defined over the closed interval a comma b. Now, Ft and Gt are two solutions of this equation. Then Pt times Wronskian of f and g, which is denoted by W of Ft comma Gt and is defined as the determinant. First row of the determinant consists with Ft and Gt, second row consists with f dot t and g dot t. So, we can prove that if Ft and Gt are two solutions of this problem, then Pt times Wronskian of f and g is equal to constant. What is the proof? ft and gt are two solutions of 5, that means this equation. Therefore, we can write pt times f dot t whole dot plus qt ft equal to 0 and pt times g dot t whole dot plus qt gt equal to 0. If you multiply this equation by gt and this equation by ft and then subtract, actually you need to multiply second equation by ft first and then subtract this by gt and subtract the product of this, that means when this is multiplied with gt from when this equation multiplied with ft, then you can find this result, that is ft times ddt of ptg dot t minus gt into ddt of pt f dot t, this is equal to 0. Actually you can see when you multiply this equation by gt, so you have this term here qt ft gt, and if you multiply this equation by ft, then you will be having here qt into ft into gt. So this qt ft gt cancels with this qt ft gt here, and you are left with ft times ddt of this minus gt of ddt of this, this is equal to 0. And if you verify, that means if you consider the derivative of this entire expression, then what will happen, f dot t g dot t will cancels with each other, those are coming from this term and this term when ft and gt are differentiated with respect to t. So you can verify that this expression is nothing but is equal to this one. So what you are getting here, that is ddt of pt times ft g dot t minus gt f dot t, this is equal to 0, and ft g dot t minus gt f dot t is nothing but this determinant, that is we have defined here and is denoted by w of f comma g. So therefore upon integration you can find pt times w of ft comma gt, this is equal to constant. Now if we find two distinct functions xt and yt which are defined over the closed interval ab and they are continuous, these two functions are said to be orthogonal with respect to a continuous weight function rt if their integral, that is integral a to b rt xt yt dt is exactly equal to 0. So therefore for two continuous function xt and yt, if this integral is equal to 0, then you can say they are orthogonal to each other. Now this is the theorem. Now consider the Sturm-Liouville boundary value problem with all relevant assumptions. For the parameters lambda and mu, of course lambda not equal to mu, xt and yt be the corresponding solutions of Sturm-Liouville boundary value problem. In other words, lambda comma xt and mu comma yt are two eigenpair for the Sturm-Liouville boundary value problem. Now if pt times Wronskian of xt yt evaluated at a and b is equal to 0, so that means pb times w xt yt evaluated at b minus pa times w of xt yt evaluated at a, this is equal to 0, then these two functions x and y are orthogonal to each other. Proof is straightforward. Xt is a solution of the Sturm-Liouville boundary value problem with parameter lambda. So you have this equation. Mu when replaced in the place of lambda, then the solution is yt. So you have this second equation. Now you multiply this by xt and this by yt respectively and then subtract, then you will be having lambda minus mu rt xt yt is equal to this one, and again this quantity is equal to ddt of pt times Wronskian of xt and yt. Then integrating from the range a to b, you can find lambda minus mu into integral a to b, this equal to this one, and we have assumed that if this is equal to 0, and since lambda not equal to mu, so therefore we have this integral is equal to 0. So that means they are orthogonal to each other. So the idea is that if this is equal to 0, then these two functions are orthogonal to each other with respect to the weight function Rt. When you look at this proof, then you can see that in order to derive the result, ultimately we came down to this particular step where integral involves this particular term Rt, and that is why this Rt weight function is required in order to define the orthogonality of two functions. So that means when we are defining two functions are orthogonal to each other, we need to define that this is Rt times xt yt, its integral from a to b is equal to 0. Now the next question is that you can think about the fact that when this will be equal to 0. I am not going to give you the detailed proof, but you can try to prove it at your own. That means suppose you are considering this boundary condition, only this boundary condition, then you can easily prove that Pt times Wronskian of xt and yt evaluated at the two endpoints a and b, and if you take their difference, this will be equal to 0. I am giving a simple clue. Here it is mentioned that m1, m2 cannot be simultaneously equal to 0. Similarly, m3, m4 cannot be simultaneously equal to 0. So as a starting point, you can consider just m1 equal to 1, m2 equal to 0, m3 equal to 1, m4 equal to 0, from where you can derive with these boundary conditions. So it reduces to xa equal to 0, xb equal to 0, and then you can prove that Wronskian of this quantity when multiplied with Pt and evaluated at the point a and b and their difference is exactly equal to 0. Now a particular example. So this is a Sturm Liouville boundary value problem defined over the interval 1 to small b, and of course b is greater than 1 is a real number. So if you compare with the given equation, then your Pt is equal to t, Qt is equal to 0 and Rt equal to 1 by t. If you use the transformation ln t equal to z, that means changing the independent variable, then you can find the transformed equation as d2x dz2 plus lambda x equal to 0 subjected to x0 equal to 0 and x ln b equal to 0. If you solve this equation, then you can see there is no non-trivial solution for lambda less than equal to 0. For positive lambda, you can find this is a solution where C1, C2 are two arbitrary constant. Now using the left hand boundary condition, you can find A exactly equal to 0. Right hand boundary condition gives this is equal to 0. We are looking for some non-trivial solution, so that means C2 not equal to 0. This will give you the eigenvalues lambda n equal to this one, and correspondingly you can find the eigenfunctions xn is equal to this. Now if you consider two different quantities m and n, that means m not equal to n, so therefore you are considering two eigenvalues lambda m and lambda n, which are equal to m pi by ln b whole square and n pi by ln b whole square. So then these two are eigenfunctions, that is sine of this part and sine of this. These are actually two eigenfunctions. And then if you consider this integral, that is 1 to b 1 by t sine of this times sine of this, then after again change of variable you can prove this is equal to 0. So hence these two functions are orthogonal eigenfunctions with respect to the weight function 1 by t. Now if you calculate integral 1 to b 1 by t xt whole square dt, after some calculation it will give you ln b by 2, and if you divide this function, that is sine of n pi by ln b into ln t by square root of these quantities, then you can have this phi n t equal to this one. This is actually the corresponding orthonormal set of eigenfunctions, and That means instead of xn, if you consider the integral, that is a to b, in this case 1 to b, integral of rt into x phi nt whole square dt, you will be getting this is equal to 1. So that means when the eigenfunctions are divided by their norms, so then you will be getting set of orthonormal eigenfunctions from the set of orthogonal eigenfunctions. So for Sturm-Liouville boundary value problem, you will be having orthogonal eigenfunctions, and from there you can easily derive the corresponding set of orthonormal eigenfunctions.